So this is the last thing we did in class on Wednesday. We took a look at some properties and we showed that matrix multiplication is associative and distributive, and it has an identity, multiplicative identity. And then we did one of these examples where we had to find conditions for a 2 by 2 matrix to be commutative with a particular kind of matrix or a particular matrix. And that was the last thing we did. So that's where I kind of just want to put the conditions back, or the properties back, and then start from there. I'll just say from last time here, and then we'll move on. This, I believe, is in section 3.2. Yep. We're kind of in the middle, maybe the tail end of 3.2. And then I don't know if I threw the transpose in, but that's the next set of business. So a transpose of a matrix is essentially switching the rows and the columns. And depending on what book you're looking at, I think it's usually denoted with a capital T, or maybe sometimes a little t, a lowercase t. So I think the transpose was defined already as the idea of switching the rows and the columns of a matrix. But here are some properties that are involved in the transpose. It turns out that the transpose of a transpose is back to the original matrix. That's interesting. Or if you switch the rows and columns, and then you switch the rows and columns again, you would get the original matrix. Right? That kind of makes sense. These other ones are a little bit more, they're a little bit more involved. You got the sum. The transpose of a sum is equal to the sum of the transpose matrices. And then a transpose, if you are multiplying by a scalar, is going to be the scalar times the transpose of the matrix. Now here's an interesting one. If you have a product and you take the transpose of that, then that's equal to the product of the transposes, but in opposite order. The order is switched. It looks innocent. Yeah, I think it might be important for later work that we might need to do. And then this is R is a power. It says that the matrix raised to a power, the transpose of that is the transpose raised to that particular power. So these are interesting properties for us to take a look at. And they might be interesting to prove as well. So let's see if we can pick one to prove. Let's prove B. Let's try to prove one of these properties. So we have the sum of the transpose of the sum. So we have to take the sum of a matrix and then take its transpose. Let's establish a couple of things. Let's say A is going to be the matrix. Remember this notation, IJ? And what that would represent is each element in the matrix in the appropriate ith row and jth column will have a different number. Sometimes people put the subscripts I and j and the i's outside as well, but I don't think we need to do that. And to find A transpose, what would A transpose be? A and then ji. That would be the transpose. So what we want to do is we want to, in our proof, we're going to say let A equal to Aij, and we'll let B equal to Bij. And then what we're going to get here is we're going to get the A plus B is what we're concerned about. So A plus B is going to be Aij plus Bij, where you're adding component-wise, right? You're adding component by component. And sometimes we just say Cij to represent each of those components being added together. So Aij plus Bij is going to equal a Cij for the different i's and j's that we have. Okay? So we'll take the transpose of that. A plus B. Oh, let's call this C, by the way. Capital C is your resulting sum, the addition of the AB matrix. So if we take the transpose of that, this is equal to C transpose, which is equal to C Ji. Okay, so that's the left-hand side of the equation. What I want to do at this point, let's say put little c ji in parentheses to say that those are the components. So this is the left-hand side of the equation. Let's say LHS, that would be the left-hand side. And so if we take the right-hand side of the equation, we should somehow get it to equal to the same thing. So we have A transpose plus B transpose is what we're adding up, and somewhere along the line we should get, one of these things so that they would be equal. So if A and B are equal to A sub ij and B sub ij, then the A transpose would be A sub ji plus B sub ji being added together, right? So this is equal to what's it equal to? Aji plus Bji, which is, I think, what we called Cji. So what we're saying is that now we have met somewhere in the middle. We took a look at the left-hand side and we tried to simplify it. We took a look at the right-hand side. We tried to simplify it. And we got these two things to equal to each other. So this is our proof. Right? And what do you put at the end of your proof? QED. Yeah, I don't know if that has a special name when you prove something coming from the left and coming from the right. I don't think that's a name. This is just a regular deductive proof. A deductive proof is something that you would look at the facts that are around you and then work things out, and then you get something that's eventually true. So there's three kinds of proofs that I'm familiar with. There's probably a lot more, or they're probably named a lot more, but just a regular deductive proof, proof by induction, which is what we did one time, and then proof by contradiction, which is to assume that something is, to assume the opposite of what you're trying to prove, and then somewhere along the line there's going to be a contradiction in your logic. And so I'm sure there's a lot more names for a lot of different kinds of proofs, but I don't know them. All right. So we have a couple of other theorems that that uses the transpose ideas, and there's a theorem that says if you have a square matrix and if you add a matrix A plus its transpose, then the result is actually a symmetric matrix. That's probably an interesting one to prove. And then I don't know if we should try to prove that one. And then for any matrix, if you have A times A transpose and A transpose times A, that those should be symmetric matrices as well. They're not necessarily equal. You can't assume that they're equal to each other because remember that matrix multiplication is not commutative. But what you can say is that they are actually symmetric matrices. Remember what symmetric was? Across the diagonal. I don't know. I'm kind of interested in proving this one for some reason. Let's see if we can prove it. Let's see if we can prove if A is a square matrix, then A plus A transpose should be symmetric. So let's see. We got, let's let A equal to this Aij business again. So if you take the transpose, if A is an n by n matrix, then the transpose is also n by n. So that way you can make sure that you can add them. Yeah? I suppose you can say that. So we can say let A be equal to this, and it's a square matrix. Then we can say A transpose is going to be Aj. And then let's add them. Okay, so what we need to do is we need to examine what these things are going to equal to. So let's see. Let's call it Well, kind of. So let's call this Cij. Now this is where you have to really watch out for your subscripts. So let's take a look at our subscripts. The I and j element, the ij element of your resulting matrix corresponds to the I and j element. Maybe if I use different colors. I don't know if that helps. But the I and jth element, or the ijth element of your sum of your resulting matrix after you add, corresponds to the ij element of A added to the jith element of A. Okay? So let's take a look at the C sub ij element. Turns out that the diagonal isn't going to be that big of a deal. It doesn't matter what the diagonal is, right? I have a feeling I should use like different CII, yeah. So that for this CII, what I mean is I want to look at the C11, C22, C33, etc. Okay? So what am I looking at? The diagonals. These are just the diagonal elements. So CII tells me that this is going to be AII plus AII. So that's just 2 times AII. So the resulting diagonal of your new matrix is going to be twice times each of the diagonals of the original matrix. Right? Yeah? Okay. Well, we're kind of here already, so. Okay. Well, we're here already, so you can prove it that way if it comes up on the test if you want. All right, so this is CII. Now let's take a look at, let's make a note here that these are the diagonals. And let's take a look at Cij. So Cij, that's how we came up with the sum, right? Is equal to Aij plus Aji, right? So what I want to do is I want to compare that with Cji. So now Cji, I'm switching the I and j indices. So if I switch the I and j indices for the first one, this would be Aji. And then if I switch the I and j indices for the second one, that would be Aij. Right? So there's an index switch over here. But these two things are equal. So that we can say Cij is equal to Cji. Ij equals to Cji, which then completes our proof that this is symmetric. Okay, remember, a symmetric matrix is that the Ij and the Ji are equal to each other across the diagonal. So this is we're done. This is when we're done. QED. The CII would be the diagonal. So wherever I see an I for the pink highlight, that would be an I. And the J, in this case, changed into an I. So the J, CII will be AI, and AII. So if I'm looking for the diagonal of the new resulting matrix, wherever I see an I here for the first slot, I'm going to replace it where the I should be. Where the I should be according to this definition or the sum. And then wherever there's a J in this slot,
plugging it into what we said was
it's okay. So we might have been better off taking a look at an example of this with actual matrices, square matrices, but this would be another way of proving it. And apparently you can use this first, one of the properties up there to prove it a lot quicker, if you want. Okay? All right, so those are some properties of the transpose. There are other types of important kinds of matrices to consider, and these they didn't bother putting in the section. Instead, they put it as exercises towards the back of the particular section. So let's take a look at some of those other properties. We did talk a little bit, I think, one time. At some time, I remember vaguely talking about an upper triangular matrix. So a square matrix is upper triangular if all the entries below the main diagonal is 0. And sometimes you might see me do something like this, where there's non-zero terms in the upper triangular, including the diagonal, and then zeros everywhere else. So this is why it's called upper triangular, is because the shape that you get for the upper part is triangular, non-zero, and everything else is 0. And it turns out that the product of two upper triangular matrices are also upper triangular. So we should see if we can prove that. I don't know if we want to prove that. Well, let's see. What? What's what? What's this? This is something. Well, it's hard to partition this into different partitions aside from, it's already triangular, upper triangular. Is there another way to write a product of a matrix as row matrix? I don't know if that would work either. Yeah. Yeah, it seems like we could do it with a picture, but I was interested in doing it with the IJ business that's upper triangular. Yeah, well, hopefully. Well, let's try it. I don't know where this is going to go, but let's try it. So here's a condition for upper triangular matrices. If we write our matrix A, so let's start by saying proof here, and let's see how far we can go. We'll let A equal to Aij, where Aij is equal to 0 if I is bigger than j. So if the row where it's in is larger than the column that it's in, then it's going to be 0. And that's how you get these lower parts, right? And then let B equal to Aij or Bij, where Bij is equal to 0 if the same condition, I is bigger than j. And I think I might need this visual to try to help me out here. So this is A11, A12, dot, 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 ANN. They should be the same, or one N. A22, A2N, and then zeros down here, ANN. And then B11, B22, let me fill out the diagonals, BNN, zeros here. I hope it's not necessary. You could do it with I's and J's, or you can use previous properties that have already been shown. So these are your diagonal, these are your upper triangular matrices. Now, if we want we want the product, right? So we want the product of A, B, and we need to figure out what this is equal to. Now, the formula for the matrix multiplication here is going to be a little crazy using, I found the matrix multiplication formula in the notes somewhere. Let's look at the picture first to see how this is going to go. So it's the row, times the column, right? So let's take a look at how this is going to start looking like. So the first slot here is going to be A11 times B11, and then all these other terms here are going to be multiplied by zeros. So A11, B11. That's your first term. Let's take a look at the second term. That would be this row and the second column. So A11 times B12, A12 and B22, and then the rest of these are zeros, so the rest of them will be zero. So you'll have a couple of terms here that I'll just put star for now. And then the rest of these things, you'll probably have some other stars and stuff. Let's go to the next row. If we take the next row, it's the row and the column. So 0 times that, 0 times B11 is 0. A22 times 0, and everything else would be 0. So you see how they're all zeros there? So that's going to be a 0. Let's take a look at the second row and the second column. So 0, and then you have A22 and B22. And then going to the third row, you have 0 times something, A22 times something, and then A23 times something else. So you're going to have a bunch of somethings here going on for the rest of them. Okay? So now, if we do the third row and the first column, we'll see a 0 here and a 0, and then zeros for the rest of them. For this next term, you'll see 0 here, and no, looking at 0, 0, and something else. So 0, 0, and then the third one is going to be 0 times something else. And then when you get to the third row and the third column, and that's when it becomes non-zero. That would be an A33, B33, and then the rest of them would be. Okay, so what's important here to try to look at is to see what happens to the lower triangular part, the lower part of the matrix. And we'll see that the more we go down, the more we'll see zeros down here. And then we're going to end up with a triangular form. All right, so that's officially not the proof of this. That's our observation. So let's see if we can actually prove it. You can kind of visualize it, but this would be more like an informal proof of trying to visualize it. I don't know. So to make this a more formal proof, you need to have the definition of the multiplication. Where's the definition of the multiplication? So with matrix multiplication, the product matrix is going to be a Cij, where Ij is defined to be this. So it's a little bit messy, but let's see if we can work this out. And I think one of the easiest thing to do to begin with is to start with the diagonal and see how this would look like when we look at the CII. And according to the CII matrix that we have here, it looks like it should be this. It should look like this, right? So let's see how this is going to work. CII is going to be the sum, k goes from 1 to n, of A I k plus b k j. Instead of a j here, I'm going to replace it with an I because that's what it's supposed to be. And so this is going to be AI1 B1I plus AI2 B2I. So because I changed my I into a j, I'm going to take a look at all my j's and change it to i's. Plus dot 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 plus a I n b n I. Now the hard part to see here is that if my I is less than j for any of these things, it's either the b sub ij is going to be equal to 0 or the a sub ij is going to be equal to 0. So I think with that idea, if the subscripts are not the same, then one of these things is going to be 0. So let's take a look at the first one. ai1, b1i. So if I is equal to 1, then it doesn't satisfy any of these equations, so this would be non-zero. But if I was not equal to 1, if I was equal to 2, for example, then either aii or b, or a1i or b, if I was equal to 2, if I was not equal to 1, then either, if I was not equal to 1, then one of these is going to be 0. Which one's going to be 0? So I is just anything bigger than 1 for this case. So if I was equal to 2, I was equal to 2, yeah, so it's the first one. If I is bigger than 1, like say I is equal to 2, then A21, so A21, where 2 is bigger than 1, A21 is going to be 0. So what we're going to have here is that we're going to have everything is equal to 0 except for aii and bii. And everything else is going to be 0. Say it again. How do I what? Oh, so either the A's will be 0 on one side or the B's will be 0 on the other side. Okay? So that's the diagonal. So now let's consider Cij, where I is bigger than j. So it'll be aik plus b kj is equal to this thing. So this would be ai1 basically it's the same thing again. B1j plus AI2 B2j plus dot 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 plus A I N B N J. So we have to assume that I is bigger than j. So let's see. So if I was bigger than j, let's see if we can get to this logic. If I is bigger than j, and A and B are upper triangular matrices, then Aij equals 0 and Bij is equal to 0. Right? For both of these will hold if I was bigger than j. So if I was a number let's say I was a number like 3. So A31 is going to be 0, right? Does that make sense? A32 is going to be 0, and A33 might not be equal to 0. What? Well, if the I was bigger than j, then the Aij and Bij would be bigger than 0. That's according to the definition of upper triangular up there. I's are your rows and J's are your columns. So for these I values here, where I is bigger than j, for, let's say, so for I bigger than k, Aik would be equal to 0. What? Yeah, so for the next one, I'm sorry, this isn't a times here. This isn't a plus, this is a times. And so if k is bigger than j, then the bkj is equal to 0. And so what happens here is that all these values are going to end up, one of these a's or b's are going to be equal to 0 for all these values here, if I was bigger than j.
Here's a proof that's not so algebraic, sort of more visual. If you want to show the product is, what do you say, upper triangular, you want to know that, say, the ith column of the product has zeros after the ith place, right?
Yeah.
But the ith column of the product is completely determined by the ith column of the second term of the product, second matrix.
Uh-huh.
And if you look at that, it only has zeros after, it has zeros after the ith point.
Yeah.
And it's the coordinates that you use to do a want to look at the first I of those columns, and they all have zeros after the ith position. Therefore, any combination of them has to have zeros after that place too.
Yeah.
So, that's it.
Well, that's what we got out of this multiplication that we did earlier, is that you got non-zeros for the first whatever columns, and then zeros for the rest. And so, but we're kind of trying to do it algebraically. So somewhere along the line here, this is supposed to all equal to 0 based on this. If I was bigger than k and k is equal to, k is bigger than j. So this is going to be true for all k, right? So I is bigger than k, which is bigger than j. That says that I is bigger than j. So I bigger than j implies I is going to be bigger than some value k, which is bigger than some value j, which is the yeah, but we're running the k through, right? So
Right, and in some cases, k is bigger than I.
so for those cases where k is bigger than I, it would be bigger than j.
Right. So we don't have necessarily that much greater than k is greater than j. It's just one or the other. Yeah.
Oh yeah, yeah. So we can't say this.
But you can say that you do have one or the other.
You do have one or the other. So when I is when I is bigger than k, then one of these products would be 0, and when k is bigger than j, then the other one of the factors, the other factor is going to be bigger than 0. So for each of these terms, either A I k is equal to 0, or B k j is equal to 0. And so that would just show that everything here is going to be equal to 0. And then we'll reiterate that this is true for when I is bigger than j. So each of these terms will disappear, and that would make your lower triangular. And so this little bit over here comes back to the definition of what it means to be upper triangular. And I think we're done. All right, so I don't think this book has the proof for this, since this definition fell in the problems section. But if you try to find there's probably, I'm pretty sure that there's a more elegant proof than this. And if what? Okay. Well, there might be a more elegant proof. I don't know. There's an intuitive proof where you just kind of look at it visually, and there's a more mathematical or algebraic proof that involves this complicated looking formula. But the main thing to get out of here is, what does it mean to have an upper triangular matrix? And now that we have this, that we've kind of proven, we now know that the product of two upper triangular matrices would also be upper triangular. All right, let's take a look at some more definitions. Not necessarily. It would be like row echelon, but it's not. I don't think you would call it an upper triangular, because it would be non-zeros at some other places. The trace of a matrix. is a single number that is actually just the sum of the diagonals. And for this, again, we want to stay with an n by n matrix, a square matrix. So if we take a look at a matrix and we just add the diagonals, then that's the trace of the matrix. So here are some important properties of the trace. The trace of the sum is the sum of the traces of the matrices. And then a scalar multiple. The trace of a scalar multiple of a matrix is a scalar multiple of the trace of the original matrix. A more difficult thing to prove is the trace of a product of a matrix is equal to the trace of the product of the reverse order of the matrix. And then if any matrix, if A is any matrix, to what is the trace, to what? What is the trace of that equal to? I think we can figure out 46 if we remember back the product of A and A transpose. So I think these are all doable. And if I were to pick one to do, I think maybe I'll pick 46 since we kind of, did we figure out what the A transpose was? A times A transpose? It's what? Oh, we figured out A plus. So maybe I don't want to do 46. We could figure out what A times A transpose is. Let's do it. I don't know. We're going to get in trouble here, but let's try to. It's not so. This isn't really a proof. It's just trying to find out a formula for A times A transpose. See if we can do it. So A, so let's see, proof, that's not a proof, never mind. I'll let A equal to Aij, so A transpose is equal to Aj. And then we want the product of this, right? So A transpose is going to equal to the C Now here's where it's kind of tricky. What you need to do is instead of this is the product that you get where you have A times B, right? But instead of B, you're putting A transpose in its place. So what you're going to do with these B's is that you're going to have these B's, they're going to change it to A, and then you're going to switch the subscripts. So according to this is going to equal to the sum of k from 1 to n of A I k times, instead of B k j, it's going to be A j k, because it has to be the transpose, the subscripts have to switch. So this is A I1, A1, 1I plus a I2 times a J2 plus, I'll put dot dot dot. Okay, so we're looking for the trace of this. So all we're really concerned about is when the I and the j are equal to it, right? So the diagonals are CII. So let's figure out what CII is. So it's looking at the indices and making the j into an I. So this is going to equal to the sum, k goes from 1 to n, of a I k times a I has, the j has to be an I, so this is I k, right? They're exactly the same. So this is just k goes from 1 to n of a I k squared. And so what is that more explicitly? If we let k go from 1 to n, it'll be a I1 squared plus a I2 squared plus a I3 squared all the way up to a I n squared. Yeah? Where the pen is right now? So a I this one? This one? 1j or j1? J has to be j1, right? Okay. Is that better? So this is AII, and what we want to do is we want to add up A11 or C11. This is CII. We want to add up C11 plus C22 plus C33 because those are going to be the entries in the diagonal, so that's the trace. So let's see if we can summarize what C11 is. C11 equals A11 squared plus A12 squared plus A13 squared plus dot dot dot. C22 is A21 squared plus A22 squared plus A23 squared plus dot dot dot. And then we're going to add up a whole bunch of them, right? C and N is going to be A n1 squared plus A n2 squared plus A n3 squared plus all the way up to A and n squared. So what's this whole thing equal to? It's just all of these things added together. So we add them all up, right? So add them all up, and then you got the trace of A and A transpose is equal to, is there any way? No, there's no quick way to do it. It's basically adding up all the entries squared of the Aij squared. It's actually a double sum, right? Wouldn't it be? So you sum along, you add up all the rows squared, and you add up all the columns squared. So it's like squaring each of the elements in the matrix and then adding them all up. Wow. We should actually check if that's true. So what we're saying here is that if A was equal to 1, 2, 3, 4, and we want to multiply A times A transpose and then take the trace of that, this should equal to 1 squared plus 2 squared plus 3 squared plus 4 squared. I don't know if that's true or not, but let's figure it out. Let's see. What's Mathematica? All right. Let's start off by defining your matrix A. 1, 2, 3, 4. So that's your matrix. We take the transpose. Of A. Transpose is just switching the rows in the column. Now let's multiply it. Oops. Let's make this into matrix form. So what's the trace of this? Trace A times oops. What happened? Trace. Oh. Well, we don't need to do that. So A times A transpose in this case is 5, 11, and 11, 25, and then the trace is 30, right? So what's 1 squared plus 2 squared? Did you guys do that one? That's equal to 30 also. So it worked out. So in our example, we got A transpose is equal to 5, 11, 11, 25. And then so the trace, according to this, is equal to the trace. So here we found a formula for the trace of A times A transpose. And if you're interested in finding the trace of A times A transpose, all you got to do is you square each of those elements and you add them all up on the whole matrix. All right, we're past time, but I'm just going to include this last bit of information here. Skew symmetric. A square matrix is skew symmetric if the transpose is equal to the negative of the matrix. So that's the last bit of section 3.2. And your homework for that will be due on Sunday. If it's...
It's already due.
Yeah, so I'm going to extend it to Sunday.
Okay,
All right, I think that's it. Oh, I had an HBA prepared, but I haven't loaded it up yet. So I'll put it up on web access, and then it'll be due sometime next week. Okay, that's good. See you guys.